So the YouTube video that I found was pretty handy for me, if you noticed, because the two topics that I scheduled for today are Moseley's X-ray uh, experiments, I guess, his work in X-ray radiation, which he did as a very young man, because as you heard, he died in the war. Uh, well, in his 20s. So it's kind of a great loss. Smart guy, did a lot of meticulous experimental work. And then the other experiment that is discussed, we're going to be discussing today, is the Frank Hertz experiment. We don't have an apparatus like that at the Naval at Washington College. We had one at the Naval Academy. It's not much of a calculational event, but it's kind of interesting to watch, and it predicts what we've been thinking if electromagnetic radiation or an electron interact near an atom. According to the Bohr model, an electron either gets promoted because it takes on a photon, electromagnetic radiation, or it gets demoted, goes from a higher energy level to a lower energy level, and it gives off a photon. And the Frank Hertz experiment is one more experimental piece of evidence that put that in place and gave credence to the Bohr model. Let's talk a little bit about Moseley's work, though. Handy YouTube video, because that particular professor, I have no idea what school she's from, but she did exactly the same lecture that I would have done. I thought she did an awesome job, and so I didn't feel the need to modify it at all. Just her 20 minutes of pre-lecture video fit the bill. But I just want to review real quick. Anybody have any questions on it? And let's take a quick look at my PowerPoint, which I would have done a video on. She did talk a little bit more about the characters involved, which I thought was funny. Some of their personalities, that the Frank Hertz, that Hertz is the nephew or something of Hertz that we have the unit of frequency for, like, kind of little interesting physics trivia. But what I want to talk about more is the problem solving aspect of it. Okay, I don't see a green border, so I'm going to stop sharing and we'll try one more time. There it is. Okay, hopefully you're seeing my screen right now. And when we talk about Moseley's work, these little spikes that are on the molybdenum X-ray curve, that's what Moseley sought to explain. Okay, we talked about Bremsstrahlung, the slowing down of an electron in the vicinity of the nucleus of a larger atom earlier. And since an electron can come in with some amount of kinetic energy and literally lose virtually any amount, okay, within the limits of energy being quantized and Planck's constant and its frequency, but frequency for an electron. We'll talk about that next week. Shouldn't have said that, perhaps, because we haven't really said that objects like electrons could have a frequency, but that's coming next week's stuff. Any event, the electron that comes in near the nucleus of an atom can lose virtually any amount of kinetic energy. And because of that, in that process of creating electrons, virtually any change is possible, and therefore virtually any frequency is possible. And that's why we have a continuous spectrum. Of course, there is that minimum limit, which would correspond to the electron losing all of its kinetic energy. But you can see we just stopped drawing the curves here, the continuous curves at about, what is that? 9.5 times 10 to the minus 2 nanometers is, I guess, what we're doing. So that's 10 to the minus 11th meters. But Bremsstrahlung cannot explain why you get these characteristic spikes, okay, the characteristic part. So when we talk about hydrogen lamps, we noted that the light or the electromagnetic radiation emitted when you excite hydrogen was discrete, had discrete frequencies. X-rays are emitted with both discrete frequencies, but also a characteristic spectrum that looks sort of like a black body spectrum, like when we talked about thermal spectrum, okay? And so X-rays have both. And we'd already talked about Bremsstrahlung for explaining the continuous part, and so today we're going to talk about the characteristic frequencies. There is a bit of nomenclature that you have to get, okay? And for any atom, we presume that even though we don't have the machinery in place to calculate what the energy levels are, we did a little bit of that last class, right? We know that that bottom n=1 energy for hydrogen is minus 13.6 eV. That's the n=1, the one that the rung right at the bottom there. And okay, then we said for all higher levels, you divide through by n squared. Well, we think all the mono electron, the single electron atoms like helium plus and lithium plus plus, ionized twice, we think they have the same kind of characteristic, that whatever that bottom rung on the ladder is here, and you calculated some of them, multiplied by 4, multiplied by 9 for helium plus and lithium plus plus. Anyway, we think that all the atoms still have this same kind of structure when the electron gets demoted from a higher level all the way down to the n=1 state. Well, we refer to that as a K type X-ray. Okay. And if it demotes from a higher level down to the n=2 state, it's referred to as an L type X-ray. And you can see n=3 is an M series X-ray, and we refer to those as a series. But then within a particular series, and let's look at that K again, that goes all the way down to n=1. Well, you call the alpha version of that K series, so it's K sub alpha, that goes from L to K 2 to 1. And you can think in terms of Rydberg's equation, what the values of n upper and n lower are then that you would substitute in. And it's, remember, it's a 1 over that number squared, okay? And because of the energy difference. And K bravo, or beta, I guess, goes from M to, from the M place, which is n=3 down to 1, K gamma, okay, n=4 down to 1, and so that's the nomenclature. And what Moseley did with this is he curve fit. He had literally was curve fitting, and he was seeing how the wavelength or the frequency, whichever you want to use. He, I think, defaulted to frequency, but they're connected by that speed of light. Okay, inversely proportional to constant proportionality is the speed of light. And he came up with a expression that related the frequency and what the atomic number of the target atom was. So he's a pretty prolific guy, right? You can see he's doing all kinds of material, whatever the atomic, let's see, atomic number looks like. That I can barely read the chart, 14, 15, something like that, all the way up to somewhere in the 40s. He did this experiment for targets with a whole range of elements. And you can see there's some that are missing right in the middle there, but still every one of these little tick marks is an element that he used as a target with electrons coming in. He bombarded them with electrons and looked for the characteristic wavelengths that were emitted. So that's his curve fit. And I'm not sure if Moseley did this or others alongside of it. They tried to make this look like Rydberg's equation. Okay, remember Rydberg is 1 over wavelength, and there's Rydberg's constant. And for the K series, remember that it always terminates on n=1. And so n=2 would be K alpha, n=3 would be K beta, etc. in this equation. And the odd thing, unlike what we did with the Rydberg atoms for single electron atoms, the hydrogen, the helium plus, the lithium plus plus, we multiplied all those by z squared. Moseley figures out, or whoever follows Moseley and works with him figures out, that it's no longer z squared, it's z-1 squared. And the reason why is, well, this idea of electron shielding. And so you've got a nucleus, say, that has an atomic number of 8. So there's 8 protons in there. The atom has some number of electrons, okay, generally 8 if it's a neutral atom. And we're looking at that very last one, the one that's sometimes called the valence electron, which is free to move. Well, it's screened by some number of those other electrons. And Moseley found when you're in the K series, just empirically, the screening is 1. It's as if there's one less charge in the nucleus because of all the other electrons. And remember, they could be on the opposite side of the atom, and that's why it's not all 7. Just turned out empirically that you subtract 1. We'll look at the L series here in a second, and it's even more bizarre number. But again, that comes from his curve fitting. And so his initial equation, that the frequency is the Rydberg constant with the speed of light, and 3/4 z minus 1 reflects that. But then where does that 3/4 factor come from? Well, if you evaluate 1 minus 1 over n squared, Moseley was only looking at the K alpha for all these elements. If you look 1 minus 1 over 2 squared is 1 minus 1/4, which is 3/4 for the specific case of K alpha. And so I would urge you, if you have a piece of paper right now, because this is going to go away when we start the worksheet, copy down this equation, 1 over wavelength for the K series, because everybody's going to do a K series problem here on the worksheet once we break up into groups. So 1 over lambda K series is equal to the Rydberg constant. I'll give that to you here in a second if you don't have it and don't remember it from last class. Z minus 1 squared, 1 minus 1 over n squared. We're now, n could be any of the upper energy states, not just 2 to 1 like the alpha series, the alpha transition in the series is, but beta would be 3 to 1. You see the point, gamma 4 to 1, etc. All right, so that's his work with the K series. He did exactly the same thing with the L series, and that's the other curve that he was in. You can see he's very prolific, a whole bunch of different elements he worked this for. Remember, L series terminates on n equals 2, and so his initial work was with the L alpha, which is the 2 adjacent states, 3 down to 2. Okay, and this is the equation he gets, and now you can see it reveals that screening of electrons, and for whatever reason, 7.4 is the number of electrons which screens out the protons which are in the nucleus. And it's a statistical number, obviously, and he got it literally from curve fitting, from extrapolating out. I guess if you plotted what he's plotting here, the square root of frequency as a function of atomic number, it would be the y-intercept, wouldn't it? Okay, if I got that, or it's the x-intercept. Now it'd be the x-intercept, wouldn't it? Because we're plotting. Yeah, it would be the x-intercept is what would give you that 7.4 number. So he just worked it out that way. Kind of bizarre. Okay. Any event, remembering that all the L series terminate at a lower state of n equals 2. So the electron goes from n equals 3 to 2 for the L alpha, 4 to 2 for the L beta, and so on. You can generalize out his initial equation for the L alpha series for any of the transitions in the L series. 1 over the wavelength for the L series, Rydberg constant, that screening factor, not z squared, but z minus 7.4 squared. And then the final state is 2, so I'll just put it in there squared, minus the upper state that the electron is coming down from. Okay, and the reason 536 up in Moseley's original work for the L alpha is if you put 3 in there for n, I've squared the 2 already, you'll get 3 squared is 9, common denominator is 36. So I guess it's 936 minus 436, which is 536, and that's where it comes from. I think I did that right? So it'd be 936, 436. Yeah, the difference is 536. And that's where that factor comes from. So that's Moseley's work in a nutshell. And I'll have a couple questions on that before we go do problems. I want to just briefly touch on what we learned about Frankenhertz. And so in come these electrons across this area. All these guys have these glass tubes, right? And they put big voltage plates across opposite ends of the tube. In this case, Frankenhertz put mercury vapor in the tube. And they noticed that if they were to excite these electrons so that they jump off the plate and then they accelerate them to the other side, okay, in the vicinity of, in this case, mercury, because mercury has a ground state to a first excited state that was exactly 4.88 volts, they came to find out. if they accelerate with greater than 5 volts, the electrons would lose energy. Okay, 3 volts, which would correspond to 3 electron volts of kinetic energy, right? They would conduct elastic collisions with the mercury. And if they conducted elastic collisions, you know that in an elastic collision, no energy is lost. But if they got more than 4.88, like 5 volts, the electrons would conduct inelastic collisions, and they would literally, in the collision, promote an electron from the ground state up to one of the upper states and lose exactly that amount of kinetic energy. And so while they're pumping up the voltage, expecting the kinetic energy of the electrons to increase accordingly, once they hit that 5 volt threshold after the 4.88, which is the difference between the ground state and what we're calling the first excited state, they would find that the electrons were actually losing energy. And so you can see a series of this happening. Okay, there's the first one right after a 5, where they would start losing energy because of the inelastic collisions, not elastic collisions. They continue to pump up the voltage, and it would go until it was double 4.88 volts, 4.88 electron volts of kinetic energy, and that would represent 2 collisions. And so the electrons would be having inelastic collisions where they'd be losing kinetic energy twice. And each of these peaks represents more collisions of the electron. Even though it has more energy, it has the ability to have more collisions with more mercury to promote more electrons over that exact range of 4.88 electron volts, and they would lose energy because of those elastic collisions. And so that's the Frank Hertz experiment. All right, so here's a couple questions for you. Any questions for me? All right, so I've got these polls set up, hopefully, and if anything's good here, yep, it looks like they're still here, just where I put them. I want to launch this poll, and a little bit on that nomenclature that I just talked about. What's the answer here? L series. What does that mean? One more person and we're done. Somebody's not playing here. No, don't go scrambling. All right, you've forgotten. All right, well, most of you remembered. Share the results with you. Yeah, it is 2, right? And if kind of a picture, you don't have to memorize it, but if you look at this particular slide right here, L is this series right here that terminates on L equals 2. So an electron that is in the N equals 3 state goes down to 2, 4 state goes on to 2. And remember, all of these N's correspond to a particular amount of energy in EV, and it's getting more negative as you go downward. So it actually loses energy from a smaller negative number to a larger negative number is in this transition, and it emits a photon because of that. And that's the L series. All right, let's move on to the next one. Moseley 2. Now you got to fill in the 2 blanks. Okay, so now I want to know about that K beta. Where does it start? Where does it end? That's funny. K beta, not L beta. All right, everybody's in. Yeah, I'm going to share the results with you just because I'm a miserable failure at explaining things. Either that or you just tune me out like my kids used to when they were your age, which is expected, I guess. Let me draw here for just a second. And again, just these kind of non-evenly separated energy states. 1, N equal to 3, And so the first thing about a K is Ks go down all the way to 1. So the only possible answers are those. And I'll just draw the first 3. There's more, obviously. Okay, so that's a possibility. That's a possibility. That's a possibility for K, because that's what K means, goes down to N equals 1. Okay, and so let's see. Labeling these, because there's a pattern, alpha, beta, gamma, okay? And so we're asked for beta. Beta looks like it goes from 3 to 1. So there it is. Okay, so those of you, and that's the minority view, oddly, like a good Tom Cruise movie, the minority view, the 2 of you that picked that one, you got it. For these folks, 2 to 1, I guess that would be a K alpha, wouldn't it, in our nomenclature? And from 4 to 1, nobody picked it. From 4 to 2, let's see, what would we call that? These are L series if it terminates on 2. If the electron goes from some higher state down to 2, that's an L, that's an L. I would call this L alpha, and this would be called L beta, right? So the letter E there, that's L beta that some people picked. All right, so you can see the 2 things. One is the number you went off in the alpha direction, and then a couple of you went off to the L direction. So just, you don't have to memorize it necessarily, but it's not that hard. It's not that hard, and hopefully makes some sense. And I didn't do it. And in fact, I don't even think I would call the person who did this a physicist. I think the chemists and the people who were doing spectroscopy, they liked that. Why they had to confuse the world by calling this the K shell, call this the L shell, call this the M shell, is beyond me in the first place. Why not just call it N equals 1, N equals 2, N equals 3, N equals 4, and be done with it? But somebody had to decide that we had the nomenclature there, and that gives students something else they have to learn, perhaps. All right, next one. I got a couple more of these. I'll stop sharing with you. And this is a little bit on the Frank Hertz experiment. And the key number, which I just said, of course, for that transition between the first 2 states, 4.88, right? EV. That would be between N equals 1 and N equals 2. So if you thought of that as being 0, perhaps, it's actually going to be a negative number. This is 4.88 above. And 2 more people to come in here while I'm yakking. All right, and the answer is, so there's somebody, we're all in. The answer is elastic, right? Elastic means energy of that electron is conserved. An elastic collision, something comes in, hits something else, the 2 fly off with conservation of momentum and conservation of energy. The kinetic energy of the 2 particles before the collision is the same as after. In an inelastic collision, the particle gives up some energy. Okay, normally if you think about collisions between things like cars, maybe the carts on the lab in Professor Tech's lab, you lose energy because the carts stick together with Velcro and they make noise and all that. Here, the reason energy is, and that causes energy to be lost. Here, the reason that the energy is lost is because an electron, which is in this lowest state, which a physicist would call the ground state, it gets promoted up, and then that much kinetic energy is lost by the incident electron. And so that's why we call that, we call it an inelastic case. Once you exceed 4.88 electron volts. Until you do that, it's going to only collide elastically, and that's the point. All right, and so let's end that. Oh, I didn't share it with you. Most of you got it. A couple of you still didn't see it. Okay, stop sharing there real quick, and we'll go to the last one. All right, come on, roll down. Stop. I have to stop sharing first, I guess. Stop sharing. And let's roll all the way down. There it is. Now it's rolling to the last one. I can launch it now. And first two people that got it. So think about that curve. It's doing something like this. One more person. And we'll give you a second to mull it over. It's not that, maybe we lost them. All right, everybody's in now. And, well, I think the right answer has to be 3, because if you remember, the magic number for mercury, which we said twice now, is 4.88 EV, just almost 5. And so so right here, there's one collision, okay? And so that would be right around, somewhere just shy of 5. Okay, then the second collision, that's around 10. And then, of course, the third equation is right around, third collision is right around 15. All right, so that's it. Any questions on that? If you're one of the people that have been getting some of these wrong, that lady's like the female professor from wherever she's from. I wish I knew where she was from. I'd send her a thank you note for saving me some time. She described this quite nicely. If it's still not making sense, it's about a 20-minute video on YouTube. Worth the watch. All right, shift over here. Stop sharing this with you, and let's go over to the worksheet for today, and we'll break up into groups. And normally I just give you one problem. Today there's 4 problems here. Everybody is looking at the K alpha line. All right. And the other constant you're going to need, I think, to answer this, I told you, right, scroll down that equation real quick. The other thing you're going to need is Rydberg's constant. And I'd go with Rydberg infinity. Why not? These are big molybdenum, almost infinitely massive nucleus. 42 protons, probably about 42 neutrons as well. I'd have to look at the atomic mass to know for sure, right? Because the atomic mass is the sum of protons and neutrons, but generally they're close in number, okay? And let's see, the Rydberg constant of an infinite mass nucleus would be 1.09737. Not a number I had to memorize ever. You would neither, and that's times 10 to the 7th. And the answer on units, though, is inverse meters in order to get you that wavelength you need. In any event, I would use that in all your calculations with the molybdenum line. So you got a Z, you know that it's a K alpha line, so you know what N initial and L final is. That one you're going to look up yourself. And in problem 1, you know that you want to get the wavelength, and you know that it should be somewhere around that number. See how close it turns out to be. And then the next thing I've got, let's stop annotating and get just a mouse back, is, let's clear those. And hopefully you've got that number written down. Target metal this time is unknown, and all you know is what the wavelength that is emitted when you bombard this target metal with electrons. And so work backwards, figure out what the atomic number is and what the metal is going to be. And I'll give you a little periodic table here in a second. But as a kind of a side note, this is one of Moseley's contributions to the periodic table, because for these next 3 metals you're going to look at, okay, this one here, number 2, is that wavelength, 0.166 nanometers. Some of you are going to look at the next element up, I think. Maybe not. Maybe it's the next element down. 0.179 nanometer X-ray emitted, and then last one 0.154 nanometer. Moseley was able to take the periodic table, which chemists at the time were ordering based on atomic mass, and say, no, that's not the right order. We really want to order them on the basis of atomic number, because atomic number is what determines what the element is, right? Everything that has 2 protons is helium, whether it's helium with 3 electrons, helium with 2 electrons, helium with 1 electron, helium with no electrons, it's an alpha particle. If you throw on another neutron, it's still helium if it has 2 protons. It's just either an isotope or some kind of ionized version of helium. Okay, and so that's what Moseley's contribution is. And so those are the 4 problems. Here's the one everybody gets to do using that 4.88 volts for mercury, electron volts if you're looking at energy, right? Because it is an electron going through some particular voltage. What I want to know is what is the wavelength emitted when it goes between any of these, between the ground state and the next excited state up, which is 4.88 EV, higher in energy. What's the wavelength? Everybody should do that one, and it's probably the simplest question that's out there. All right, so let's see. I've got just a few minutes after. We'll give you about 10, 15 minutes to do this. We'll come back and we'll declare our numbers and break up into groups here. Oops, somebody's chatting at me. Oh, there you go. Silly chemist. Yep. All right. So nothing, but I'll get breakout rooms. We'll go, since you got 4 problems and then everybody's doing that 5th one. Okay. So room 1, Prince and Saeed, Amaya and Shneha in group 2, Anaya and Sam in 3, and Justin and Max, you're in 4. Max, it always seems to put you in group 4. Not sure what that is. All right. We'll see you in a little bit.
It's actually like we have all day to.
Dude, I love these classes. I don't know for what reason, but they just feel so. We feel like we get so much work done because it's broken up into so many sections.
What I wish, though, is we had like another 15 minutes.
Yeah. No, even with this, like, it feels really long because other classes you just stare into a screen for like 40
right.
straight.
Yeah, I look up and I go, shoot, it's already noon. Yeah, wish we had more time. And it's, if you like physics, it's neat stuff too. All right, yeah, I broadcasted that out just so everybody's got it. So what are you guys going to start with?
I'm just looking at. I'm just trying to read the question completely. I got some notes from you over here.
There you go.
We're using the formula, right?
Yeah, just take that formula. You can use that one if you want. And different people will do this differently. The one right there, that the frequency of the K alpha, you can use that one. Or you can scroll down the one you highlighted right there. You can use that one, whichever one you prefer, because they're equivalent. One's going to give you wavelength, one's going to give you frequency. That's the only difference.
Professor, I had a quick question. The
Sure.
C, what does the C in that formula stand for?
It's still the speed of light.
Speed of light times the constant.
It should, times the Rydberg constant, which you've got written right there. R is the Rydberg constant.
This definitely seems like a simpler one. This one is
simpler, but I think the problem gives you wavelength, right? Or asks for wavelength. So once you get frequency, you'll have to take frequency divided by wavelength.
Yeah, true.
So it's
It's basically the same, honestly. It's
It's
not
really the difficulty's
Yeah.
pretty much equivalent to me. So whichever one you want to use.
All right. Okay.
All right, I'll leave you guys alone. Moving on to the next
Awesome.
group.
Thank you.
You bet. So I can figure out how to get out of here. Join the next one.
Seven. Seven? Seven, yeah.
Plus 7, right? Plus 7.
Plus seven?
Plus 7. Yeah, plus 7.
Plus 7. Z minus 1 squared. 3/4.
Yep.
Okay.
Which is 3/4.
Okay, so Z minus 1 squared equals.
All right, you're on the road. You got it. I'll move on to the next room.
Equals 1 by 0.166 into 10 raised to minus 9. That 1 by lambda number you put.
Hey,
What
just
range?
checking for 3. Is it cobalt?
3 cobalt. Yes, it is.
Okay, so we'll keep doing the quadratic equation thing. So Z
so-
squared.
How'd you know that? Did you just guess?
No, I did the work earlier before class.
Okay.
Let me check.
Okay. Yeah, so you should figure out that Z is equal to cobalt's atomic number.
So
Yeah,
Z squared minus 2Z minus 678 point something something. That's the quadratic equation I solved Z for.
Just a piece of advice.
My two.
Just solve for all of this. Where's my tool? Solve for this. Take the square root and add 1. I think it's just easier than the quadratic.
I put it in a online calculator.
You could, I suppose. But what I would recommend you do is, solve for that, okay? And then get a number, and then take the square root of that number, and then add 1 to that number. It's that way you don't need a calculator. Well, an online quadratic calculator, all right? But you can do it either way. You're not wrong to do it your way. Not wrong.
Okay.
I just think that's too much work. All right, I'm going to the 4th group.
All right.
Thank you.
You bet.
So rounding down, that would be 28, which would be nickel.
20. Which one? You're doing 4.
Yeah.
Hold it. Isn't this? You did a math. You can't do what you did here. I'm going to correct your 9th grade algebra. You can't do that. It's still Z minus 1 over here squared.
Okay.
Right? So I don't disagree. All of this stuff, when you take the square root, is about 28 after you take the square root.
There you go.
But now what do you
That's
have
an
to
easy
do?
fix, though.
Now you have to add 1, don't you?
Yeah.
Now
So
you can add that
29.
1 on.
So copper.
29.
Yeah, copper, exactly. Yeah, it's not hard. It's not hard physics, but it's the calculation, I guess. All right, so you're off. Go off and do the 5th one now, and we'll get back together in a little bit.
Cool.
You see?
I see. No, dude, I got the answer. I only wanted this answer of yours. And I got the same answer.
Yeah, so I sent it because I usually write on paper. So
No, that's great. So yeah, we're doing nanometers. Okay. So I got it. Now the question I want to clarify for myself. So both methods work. They got to the same answer. But I just want to know what is this 3/4 about? I just don't.
What is that 3/4?
Yeah, that's my question.
Here's what I think. This is supposed to be n, which for k alpha is equal to 2. So it's 1 minus 1 over 2 squared is 4, right?
Yeah.
And that is 3/4. So this whole thing right here is equal to 3/4. 1 minus 1 over 2 squared.
I see exactly what you're talking about. Yes, that is correct. But here's the funny part. I plugged in 3/4 inside there.
It still worked. So that's an interesting question. So what's 1 minus 1 over 3/4
I take it back.
squared?
I think I plugged in 3/4.
So this would be 1 minus 16 over 9, which is still, so that would be 9 over 9 minus 16 over 9. 5 over 9, it's probably got you close enough. 5 over 9 is probably close enough to 3/4 that you still got the right answer. No, but it still came out to 3/4. I don't know. It's an algebra problem there, like just a calculator problem.
No, you're right. This actually. Oh wait, let me write it as the proper form.
Yeah.
So it would be 2 squared. No, I got the answer. It's actually not the same. So with the other one I just wrote, the answer would have been 0.069.
Yeah, and that's the difference between 7/9 is not exactly 3/4. When you use exactly 3/4, you get the right one. So yeah, I think that's the issue. All right, go ahead and do the last problem then. It should be pretty quick. I'll give you a hint on the last one. E is equal to HC over lambda.
You mean fifth one or fourth?
Yep, number 5 there. Yeah, everybody's doing 5. So 1240 EV nanometers divided by the wavelength, solve for the wavelength, and you should be good to go. Should take you just a second. That equation comes up all the time, doesn't it? Yeah, and the answer here is...
You mean 1240, right? Yeah.
Yep, 1240, but this is 4.88 EV. All right, how are we doing on time here? I'm going to leave you guys.
All right, thanks.
All right, 254.1, I agree. All right, you guys can head back to the main room. Everybody else is just finishing up number 5 as well. right. Is everybody back? Yep, now everybody's back. Good. Okay, so I don't know if there's any value in presenting. Nope, we're still missing somebody. There we go. There's Prince. The one question that I did see is which equation do you want to use to solve each of your problems? And some people like this one right here, and that's fine. That'll give you frequency. That K is a little big. That's a subscript. The other option, of course, is to, why am I making marks there, is to go on and use this equation. I guess I could stay here, use that guy. They're equivalent, so you can use either one. Remember, this one gets you a wavelength, whereas this one gets you frequency. And so I think each of my problems either asked for a wavelength or gave you a wavelength. And so I think the second one here down at the bottom is probably the easier one to use. But that's style, and you can do whatever you want. You do notice that if you bring this C over to the other side of the equation, well, you get 1 over wavelength, don't you? So they're pretty equivalent. In any event, I think the first one was, if you calculate the wavelength given molybdenum, which is Z equal 42, you get a wavelength of 0.072 nanometers. And the rest of you were given a wavelength and asked to find Z. No big algebra issues, but remember, I find it easier just to solve for that thing or to solve for that thing, take the square root and then add 1. Okay, there are other ways to do it, but that's the easiest way. And so the three elements I gave you, number 2, you guys should have had nickel. Number 3, you guys should have had cobalt. And number 4, you guys should have had copper. And I think that's what everybody was calculating, correct? All right, and then the last one, all you do is you look at the, you look, let's clear that. Come on, clear all my drawings there. All you do is you look at the equation, perhaps of the last 2 chapters, that the energy is equal to HC over lambda, one more time, okay? And the energy for mercury between the 2 states, the ground state and the next excited state, is exactly 4.88 EV. And so 4.88 EV is 1240 EV nanometers divided by the wavelength. And so each of the groups hopefully calculated that. I saw two of the 4. I'm going to give the other 2 credit that you got it too. It should be about 254 nanometers when you solve for wavelength right there. Okay. Any questions? I think I'm just, I was watching the confirmation hearings, and that guy Kennedy from Louisiana, I find him hysterical. He had just finished his questioning of Judge Barrett, and he goes, and Mr. Chairman, I want to point out that I've landed this airplane with exactly 26 seconds to spare. And it looks like exactly I just went over by 1 minute. So I didn't quite do as well as Senator Kennedy did. But you all have a great weekend. Any questions on anything? All right. If not, have a great weekend. There is now a new homework due next. I moved it to Wednesday, not Thursday. Let's try and meet that due date, and look for the pre-lecture video for brag scattering on Monday, and we'll see you then. And a reading quiz, of course, because what's life without that? Have a good day.
You too.
See ya.
Honestly.
All right. And let me stop.